very warm welcome, very good morning, good afternoon and good evening to all the participants and the students for this course under NPTEL MOOC, the title of which is Application of Forecasting, Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you are aware, this total duration of the course is, I am just repeating it, is for 30 hours, which is spread over 60 lectures, each lecture being for half an hour. And for this whole course of 30 hours, there are three main topics. Number one is forecasting with all the concepts we have discussed. Number two is regression models, and all the concepts we have dealt in details as we did for forecasting. And the third part is time series analysis. So, we are in the last phases of the regression, even though the title is written as multiple linear regression, is a regression models which we are considering. This is week 10, 48th lecture, and what is the coverage? Coverage would be nonlinear regression. We will just, as we remember regression models, we are just considering different examples, number one. Number two, the simulation concepts which we are utilizing are not based on any programming, very simple Excel sheet utilization. And as you keep changing the parameters, keep changing the values, you get different types of curves for the regression model under each category, and that has been quite helpful for me to explain to you the concepts based on which we are proceeding. And if you remember, the main point of trying to basically reduce the error or with the variability being the main idea based on which the models have been discussed. And if you remember, in the multiple linear regression, because the linearity concept was true, hence trying to handle and find out what were the beta values was much more easier. Now, in this concept on nonlinear regression models, trying to handle the different type of beta values, or if you see in our case for the Excel sheet as well as in the PPT files and each PPT discussion, the parameters which are to be found out, which are in place of basically beta, are the theta values. So, depending on the theta values, we can find out that what is the best fit line such that you are able to minimize the error. Error part is basically the variability. Now, before I start the exponential model, which describes an increasing or decreasing trend with constant relative rate, and the equation is given. If you remember in the last two lectures, which was 46th and 47th, the main emphasis was basically give the model and explain what are the parameters theta 1, theta 2, theta 3, depending on how many parameters are there. And then for at least 4 different combinations of the parameters, draw the best fit line which was given in blue, and then also along with that plot the values of the actual simulated, so called simulated values of that curve, considering there is an error, because the error would basically give me the idea that how the values of theta 1, theta 2, theta 3, considering there are 3 parameters, they can be adjusted in order to basically minimize the total error. Now, minimizing the total error, if you remember the error concept being there, the main idea was that I want to have an error where the expected value is 0 and the variability has to be reduced. The expected value being 0 is that more you simulate, more number of data points which you have, and if you are able to find out the best, as per the assumption, the best type of error, whatever the distribution is, then you will basically be able to handle in such a way that the expected value of the error in the long run would be 0. But the next point will immediately come up is that having the expected value of the error is 0 is good, but what about the variability? So, here what was the point of discussion which I was mentioning in few bullet points, is the idea is to have a combination of those theta values, have a combination of those parameter values in such a way that the variability would be reduced. Obviously, because there are multiple parameters, there are more than one. So, trying to optimize and try to find out some model which will give me the best combination of the theta values will take some time in order to explain and then utilize different type of models. Like iterative methods can be there, different type of simulation techniques can be there, different Newton-Raphson method can be used, Runge-Kutta method can be used, different type of mathematical analysis. Because this is a course where too much in depth going into the in depth of theoretical derivations would not be warranted. Hence, I have only giving the actual results with considering that different type of parameter values, how they are changed, how does the best fit line with respect to the simulated actual data would look like. Now, you may immediately ask the question that these points which are fitted, do they give for all the different type of models we have considered, do they give the best combination of theta? My answer would be no, I have not done that. The reason being that I wanted to show you that as you keep changing the values of the theta in the simple Excel sheet, you can get a different sets of values of theta, and then you can basically find out for which sets or which combination of theta you get the best fit lines as that the error is minimized. That can be taken up and you have to do some simulations in the Excel sheet, and that will give you a lot of information which I have been mentioning in the last two class, which is in the 46th and the 47th lecture. So, the emphasis which I just spoke for the last 5 minutes would continue to remain true for the other models as we tackle them. So, in the exponential model, it describes an increasing or decreasing trend with constant relative rate, which is given as. So, your actual equation is this. Your y, which is the dependent variable, is equal to theta 1 into exponential theta 2 into x plus epsilon, and where theta 1 is basically the constant being multiplied with the exponential part and theta 2 is the growth factor. The error terms, as you remember, can be either uniform discrete or uniform continuous between minus a to plus a, because in that case the mean value would be 0, number 1, and number 2, changing the values of a minus n plus a would give you different ideas about how the variability can be increased or decreased. So, minus n plus a being very small values on to the left of 0 or to the right of 0 would give you a variability which is very small. If the minus a and plus a values in the quantum sense are very big, like minus 20 plus 20, and obviously in that case the variability would be large, but still catering to the fact that the mean value remains 0. In the second case, when we consider the error, it is normally distributed with 0 mean and sigma square as the variability. So, in that simple case, you can consider sigma square as 1 and then simulated the data to basically find out that how would the error fluctuation look like considering the mean value is 0 and the variability is 1. And as mentioned, you can change the value of sigma square and have a whole gamut of different type of normal distribution, but with the mean value being 0, but the variability can be changed. Other case can be where the error can be modeled as considering the t distribution. But if you remember, in the t distribution with higher degrees of freedom, the mean value will slowly be 0 in the long run and the variability can be made as 1, which means that the t distribution can be modeled as a standard normal deviate with the mean value as 0 and the variability as 1. So, in the graphs which we will consider, I am only showcasing any one of them of these errors, and in that error component you can consider different combinations like the uniform discrete between minus a and plus a, minus n plus a you decide. You can consider in the normal distribution with 0 mean and sigma square as the variability, you can consider t distribution with degrees of freedom. So, you can play with this simulation, play with the data and at least understand how the best fit line will look like and how the variability would have an effect on the simulated data for the actual so called real data set, considering the real data set or simulated points are denoted by the red color and the best fit line is denoted by the blue color. So, this is for the exponential one, where we are plotting y and y1, y is basically the best fit line, and y1, which are the red points, are the simulated data versus x for theta 1 is equal to 5, theta 2 is equal to 0 minus 0.5. And as I told that, and as we have utilized in the last 2 lectures, we extensively use the Excel sheet. We will try to utilize the same Excel sheet for this corresponding type of different type of nonlinear regression models, which we will now discuss. So, I will go back to the Excel sheet now. Yes, so it is there. So, we are going to solve the exponential part. Let me get the exponential distribution, the exponential component part for the simulated data, and then I will zoom in such that the values are clearly visible. Let me zoom in a little bit more. So, this is the exponential one, you can see, and this is a graph which will keep changing, as you see, with for different values of parameters. Now, x are the values, and there are 124 data points which you have considered for simulation. X values are given in the column AM, y values based on the best fit line, considering there is no error, is given in the column AN. The error is given by A in the column AO, and the actual data, how it should fit for the actual data, which are represented by the red dots, is given by column AP. Now, here the error is considered as a random variable between standard, this uniform random variable between minus 0.5 to plus 0.5. You can increase or decrease it depending on what you think the error should be. Number 1. Number 2, if you remember, and I mentioned that there is a starting seed value for x also, which you are considering. So, the seed value here considered is 1.5, and the delta x value is considered of 0.1. So, you can keep changing that, the incremental values of x also. So, let us considering the first data set as the slide shows and the graph is shown there. So, let us go back. It is theta 1 is equal to 5. And theta 2 is equal to minus 0.0 is equal to minus 0.5. So, this is the data point which we have, and if I consider the seed value. So, if you see it, let us consider the delta value as 0.2 and the seed value as 1. So, obviously, if I consider a delta value of, say, for example, 0.5. So, here you see the pattern remains same, and the error terms which are shown by the dotted lines with respect to the blue line. Blue line is the best fit, dotted points are the simulated actual data. So, if I consider as 0.01 for delta, so you have this changed, the shape looks the same, but how you are trying to plot it depending on the starting value of x and the increment values of x will give you a good idea. If I consider the delta value as 0.5 and the x value starting as, say, for example, 2. So, here you have the graph with respect to the actual value with the simulated value, actual value being red, simulated actual value, and blue being the simulated best fit line. Now, the error term which you have, you can increase the values of minus a plus a. So, say for example, if I consider as 6, and how would the error look like, how would the y1 look like. Now, you see, as the error increases, the variability is huge. Now, for the error, if I keep the error fixed, can we find out, or can we change the values of theta 1 and theta 2 to at least have an understanding that the error is decreasing? So, let us do it. So, let us change theta from 5 to 1. So, the error is not changing much. Let it change to 0.1. So, error is not changing much. That means, the effect of theta 1 on the values of y 1, which is the simulated actual value, does not have that much effect. So, let us revert back to 5 and let us now do something with the values of theta 2. So, let us make it plus 0.5. So, the moment you do plus 0.5, the trend changes plus the error with respect to the best fit line and the actual value also shows a huge amount of improvement. So, let us make it as 1, that theta 2 as 1. So, obviously, now they are almost overlapping. So, if I consider this theta 1 as also 1. So, it means that the effect of theta 2 on the error term and the actual with respect to the best fit line and then the actual data has much more significance than the effect of theta 1. And if I go back to the equation, what was the equation? Equation was basically theta 1 into e to the power theta 2 x. So, theta 1 was the constant which was multiplied and theta 2 is the growth factor, because exponential component as it increases it would definitely have a much more commanding factor on what would be the type of curve which you will be getting in the nonlinear regression model. Now, in the second curve you have exponential, same thing with theta 1 as minus 2, theta 2 as minus 1. So, let us do it minus 2, minus 1 and these values, which means that I need to change the error terms, because that and also the starting values. So, here the error term, if I keep it limited to and if I take it as 1 or 0.5 and if I take it as delta as 0.1 and if I now reduce the error. So, now you will get it. So, error concept has to be reduced. So, now you see this graph and this graph are almost replicating, which means now I have to reduce the error in try to find out that for that particular error what are the best fit theta 1, theta 2. Now, the question may be asked from your side that why are we trying to basically adjust the error also, is basically we are trying to do a in-depth simulation such that we will have an understanding that how the error once fixed, how what is the best value of theta 1 and theta 2, or else we can look at the other from the other point of view, that keeping theta 1 theta 2 as fixed, we want to understand that what would be the properties of the error. Should the error be very large, should the error be very small, such that we are able to get the best fit line with respect to the simulated data as close as possible. So, both ways we are trying to understand and have a much better perspective how the nonlinear regression models with different values of thetas would pan out, would look like for different values of theta 1, theta 2 or theta 3. And also remember the another two things are under your control. One is the delta x value and one is the seed value based on which you are starting the x increments or the x values which you are reading. So, all this combination of these three, the parameter sets, the errors and the seed value along with the incremental values of x would give you a much more in-depth information about the different type of nonlinear regression models which are being discussed. So, if I consider now, let us take the error as small. Then now you will see the errors are becoming smaller and they are replicating what the PPT slide is. Now, let us go to the third graph where we have theta 1 as 10 and theta 2 as 0.005. So, it is 10 and 0.005. So, if you see this is the curve which we have exactly the same thing, only the error or the perturbations of the errors with respect to the best fit line is less smaller. So, that would depend on how the errors have been simulated, because the simulation study, and as I said you have all these three things under control. Number 1, the set of parameters, number 2, how you simulate the error, and number 3 is basically starting values of x and the incremental values of x. In the third graph, which is totally different, which is downward sloping, we have theta 1 as -3 and theta 2 as 0.01. So, this is how the graph will look like, downward sloping. Initially it was, in the last graph it was upward sloping, downward sloping for a value of theta 1 as -3, theta 2 as 0.1, and starting seed value x is 0.5, incremental values of x is delta x is 0.1. So, this is how the graph would look like. Now, we will go to the 41st example, because you remember we are considering different type of examples. If you consider the nonlinear regression example, which is the Michaelis-Menten model, which is for enzyme and kinematic equations in chemical engineering or chemistry. The equation is given as y is equal to theta 1 into x alpha, x to the power alpha, and in the denominator you have theta 2 plus x to the power alpha. So, in the first fact you are multiplying theta 1, in the second fact in the denominator you are adding theta 2. So, there is an error term also, and theta 1 and theta 2 are the unknown parameters and alpha is the power of x. Now, as usual, as mentioned, epsilon is the error term, which is given as uniform discrete case between -a to +a, and depending on a you can have higher variability, lower variability, but keeping in mind that you are keeping the expected value as fixed, which was the main criteria of discussion. You can also have the error as normal with 0 mean and sigma square as the variance. Increasing decreasing sigma square will give you a lot of information about how the variability can be controlled, and epsilon being as t distribution with n degrees of freedom. As n increases, which I am mentioning and repeating, sorry for that, you can have the normal distribution with 0 mean and 1 as standard deviation. So, let us go through the graphs. So, this is the kinematic reaction equation, Michaelis-Menten equation model, and we are plotting y and y1 versus x, and what are the theta values? Theta values as shown in this PPT slide. Theta 1 is 2, theta 2 is -3 and alpha is 0.1. So, let us do it. So, in this, so I have to now bring Michaelis-Menten model. So, this is the Michaelis-Menten model. You have bit you have the Michaelis-Menten model, and let us go back to the set of simulated data. Yes, here it is. So, in the yes, done. So, in this case, for the case of Michaelis-Menten model, alpha is taken for the here, as you can see in the Excel sheet, 0.1, theta 2 as 2, theta 3 as theta 2 as sorry, alpha as 0.1, theta 1 as 2, and theta 2 as -3. Here the seed value of x is 5, delta value is 1. Now, let us go back to what are the values of theta 1, theta 2, alpha. Theta 1 we will consider as 2 minus 3, 2 minus 3 and 0.1. So, this is the values which I have. So, this graph which is there in front of us is exactly one which is being replicated in the PPT slide. So, if you see the fluctuations are there, both positive and negative. The fluctuations I mean this one. Go to the PPT presentation slide mode and I will explain. I will use the green line. So, consider the graph, the best fit line, the blue one. Let me use the color blue. So, it will make sense. So, the best fit line is here, right. And also I have the plots of the actual data. So, let us take few points. Now, the error term which we all know, but still I will draw and I use the green for the errors. So, these are the distance from the best fit line for the actual data. So, as we know, if these are the errors epsilon 1, epsilon 2, epsilon 3, epsilon 4, our main task is summation of these error term square and minimize it, and that minimization which we have done in the multiple linear regression model gave us that idea that trying to differentiate and find out that those values of beta which will ensure the minimum error was the main task. This is also the main task here, but considering that you would not have not those simple derivations, you will basically have different type of iterative methods. As I said, rather than going into the detailed mathematics, I wanted to show you through simulation how the idea of different type of nonlinear regression models can be analyzed. So, now we go to the second graph, which is y 1, y 2, y and y 1 versus x for theta 1 minus 0.2, theta 1 is minus 0.2, minus 2, theta 2 is 0.5. Theta 2 is 0.5 and alpha is 0.2. So, this is the graph which you have, is exactly the same what you can see in the PPT. So, you can change these values, and as you change the simulated data both for the best fit line as well as the simulated actual data points, which are blue in color and red in color, are being shown. In the third graph, we are considering theta 1 as 10, theta 2 is minus 2 and alpha as 0.5. So, this is the graph. So, here I have to basically, in order to show these errors, I have to basically consider the error concept, because here the error concept, since they are almost 0 because they are overlapping. So, let me increase the error. So, those error fluctuations would be much more visible to us. So, I take, so for all these problems, you remember I am taking the uniform discrete distribution. I can take the normal distribution also. So, what I mentioned, if you remember, keep simulating and changing these error terms, what type of distribution you will take, you will get all these values. So, if I increase the error, so it is increase has been a little bit too much. So, let us make it not that high. Yeah, here now you are getting quite a close fit. So, here if you decrease the error, obviously it will be almost a replica of what is being shown in the PPT slide. And finally, when we come to the case of the Michaelis-Menten model with theta 1 as minus 2. So, let us go to theta 1 as minus 2, theta 2 is minus 3 and alpha as 1. So, now you see the graph which is being shown here along with the one which is there in the Excel sheet in the PPT one. Here the error is a little bit more dispersed. So, let me handle the error and decrease it. So, now it looks almost exactly the same. So, with this I will close this 48th class and continue more such examples for the nonlinear regression model. And again I am repeating, utilization of the Excel sheet gives a lot of confidence in how I am able to explain. I am sure once you get that Excel sheet, you can play with the data for the nonlinear regression part, because in the Excel sheet which will be shared and some part has already been shared, there are different components. One is for the regression, one is for the forecasting. So, the regression models under that sheet you will have all these data points. With this again I am requesting, and we will finish this class, which is lecture 1, lecture number 48, and continue further discussion about nonlinear regression with other type of models. Thank you very much and have a nice day.